We have solved the central equation near the zone boundary, and we have the following wave function expansion near the zone boundary: c of k e to the ikx, c of k minus g e to the ik minus gx. So k is equal to g over 2 and k minus g is equal to minus g over 2. So that's the zone boundary solution. And by plugging this into the central equation, last time we found that we have a relationship between these coefficients. C of minus g over 2 is plus or minus c of g over 2. So if we substitute this result as a constant c0 here into these the wave functions, for the plus 1 we have c0 e to the ig over 2x plus e to the minus ig over 2x, and for the minus solution we have c0 e to the ig over 2x minus e to the minus ig over 2x. So the plus 1 will give us 2 cosine pi over ax, and minus 1 will give us 2I sine pi over ax. So g over 2 is pi over a, as you know. So that's the first Brillouin zone boundary. So these are actually standing wave solutions, and for the 1D monatomic lattice we have g over 2 is equal to pi over a. So we're considering this one-dimensional case as an illustration. Why do we have standing wave solutions at the zone boundary? Because we have the Bragg reflection condition. The k vector dot product with g hat is equal to g over 2. That's the von Laue diffraction condition, which is equivalent to the Bragg reflection condition. So we have k equals g over 2. That gives us the constructive interference of two waves, giving us the standing wave solutions. So we have the Bragg reflection of electron waves from those planes that are perpendicular to our reciprocal lattice vector G, and these two solutions will pile up the electrons in two different locations because the probability of finding an electron in a certain region in space is proportional to the magnitude squared of the wave function. So we have cosine square pi x over a and sine square pi x over a. So in our one-dimensional lattice, you can see that the psi positive solution gives us a higher probability of finding the electron close to the core. So that has basically, because of the negative charge of the electron, this has while the potential energy is high, we have, for the negative charge, we have a potential well there, so it's going to be a low energy solution. And psi minus absolute squared gives us the highest probability of finding the electron in between the ion cores, and this is going to have a higher energy. So for a traveling wave, we have the charge density e to the ikx times e to the minus ikx is equal to 1. So the magnitude is equal to 1. So that's a constant. So for the free electron theory, we're considering a uniform distribution of electrons. So that's this traveling wave solution here. But on the other hand, if we consider the nearly free electrons, then we have an alternating probability of finding the electron close to the ion cores and in between the ion cores. So we have seen that this positive solution piles up electrons close to the lattice sites, and negative solution piles up the electrons between the lattice sites. So we can represent an electron with k is equal to plus or minus pi over a, either by a wave function which requires the electron to spend most of its time near the atomic cores, or by a wave function which dictates that the electron will stay in between the atomic cores. So since the electrostatic potential is large and positive at each atomic site, we have a potential well for the electron because it has a negative charge. So that's going to have a low energy. Whereas for the psi minus, we will have a higher energy that's away from the potential well. Now, to summarize our results, in the reduced zone scheme, the nearly free electron model gave these energy bands. So we have in the first brilliant zone, first up to k is equal to g over 2 or minus g over 2, first brilliant zone, we have the solution that looks like the um, free electron solution, but here we have these energy bands. And we can see that psi plus and psi minus solutions give us the basically at the brilliant zone boundary, we find the band gap between these two solutions. Basically, that corresponds to the fact that we have standing wave solutions at these zone boundaries. So basically, we can see that we have these energy bands forming that is due to the solutions that give us the electron highest probability of staying close to the ion cores and away from the ion cores, and these band gaps are given by twice the Fourier coefficients of the potential. So for the first brilliant zone boundary it would be 2 times V, and in the second brilliant zone boundary we will have 2 times V2, which is the second Fourier coefficient of the potential. So this is in our reduced zone scheme. This reduced zone scheme was obtained by using the extended zone scheme and carrying the energy versus K plots by the appropriate reciprocal vectors back into the first brilliant zone. So that's what we have seen in the free electron case first, and this is basically exactly the same thing we're doing. So we have these energy bands in the extended zone scheme that can be transformed into the first brilliant zone by using the appropriate reciprocal lattice vectors. Now, I want to ask how many k values are possible in the first brilliant zone. So since we have energy increasing as k squared, the first thing we notice is that the higher the band, the greater its width. You can see this here. The higher the band, the greater the width. So delta E is increasing. So this is basically increasing as we go up higher in energy. That's because we have roughly k squared dependence for the energy. And the higher the energy, the narrower the band gap. So these band gaps are getting smaller as we go up in energy. So therefore you can see that the reason the band gap gets smaller is because it's the Fourier coefficients, it's proportional to the Fourier coefficients of the crystal potential, and the Fourier coefficients will decrease as a function of 1 over g. That's due to the electrostatic potential decreasing as 1 over r in direct lattice. It decreases as 1 over g in the reciprocal lattice, and we have basically a smaller contribution to the band gap from these Fourier coefficients. So as we move up in the energy scale, we're losing our band gap and our bands are getting much wider. Therefore, we're actually getting an electron that behaves more like a free particle. So the more energetic the electron, the more it behaves like a free particle. Now, on the other hand, when we look at our block wave solutions, and if we look at the periodic boundary conditions, psi k of 0 is equal to psi k of Na. So at the edges of our crystal, we should have the same wave function. This gives us e to the ik Na equals 1, and L, the length of our crystal is one-dimensional crystal, is capital Na. So we obtain k values 2 pi over Na, 4 pi over Na, plus or minus, all the way up to plus or minus pi over A in the first brilliant zone boundary. So how many values do we get? When pi over A is equal to 2n pi over capital Na, you see that n is equal to capital N over 2. For plus values and minus values, we have n equals plus minus 1, plus minus 2, all the way up to plus minus n over 2. So this tells us that we have capital N distinct states for the electron. So it can have capital N distinct values of k. So what is capital N here actually? It's the number of primitive cells in the lattice. So for each primitive cell, we have a k value. Now, if we multiply n So considering the wave vectors, we also have a spin degree of freedom. For each state we can have spin up or spin down. Then we have two capital N independent orbitals in each energy band. So this brings us to an important conclusion about the transport properties of solids. So if we have m valence electrons per primitive cell, then there will be m times capital N valence electrons that can be accommodated by these block states. So if m is an even number, then there will be m over 2 bands full at 0 Kelvin. So we can determine whether a solid is a metal or an insulator by considering the number of valence electrons. So if we have 2n valence electrons, we will have, as you can see, we have 2n independent orbitals in a band. We will have one band full. If we have 4n valence electrons, we will have two bands full, etc. So a crystal can be an insulator only if the number of valence electrons in the primitive cell is an even integer, because then we will have a full band and then we will have an empty band above it, and there is a band gap in between the two. So this will imply that there will be no states, empty states for the electrons to move into, and electron conduction will be very difficult. So this is because each band can accommodate only 2 electrons per primitive cell to fill the 2n orbitals. So as an example, diamond has atoms of 4 valence electrons, for example silicon. So there are 8 valence electrons per primitive cell. If you remember, we have a 2-atom basis for the diamond, 0, 0, 0 and 1, 4, 1, 4, 1, 4. So the band gap of the diamond is 7 electron volts, and the crystal is a good insulator because you have a full band. You have two atoms per basis and 4 valence electrons per atom. So we have 8 valence electrons per primitive cell, which is an even number, and it does turn out to be an insulator with a large band gap. However, if a crystal has an even number of valence electrons per primitive cell, it is not necessarily an insulator. It may happen that the bands overlap in energy, and if they do, then instead of one filled band giving an insulator, we may end up having two partially filled bands giving a metal. For example, magnesium and zinc are good examples. And if the overlap is very small, then we will have a semi-metal, for example, bismuth. So in summary, in one dimension, first of all, if we have m even, it's an insulator, m odd, it's a metal, but in 3 dimensions, we may have bands overlapping. Now, on the other hand, if the number of valence electrons per primitive cell is odd, then the solid has to be a metal. For example, sodium, if you consider sodium which has one valence electron introduced to the lattice, the alkali metals in general, they will have one valence electron per primitive cell. So these will be metals. And there are materials that fall in an intermediate position between metals and insulators due to the fact that the band gap between the valence band and the band immediately above it is small. Then the electrons are readily thermally excitable to the upper band, and both bands become partially filled and both contribute to the electrical conduction. So you have empty states that are forming in the valence band, and then you have empty states in the conduction band as well, but you also have some full states because some electrons got excited to the conduction band, and these are known as semiconductors. For example, silicon with a band gap of 1.1 electron volt, germanium with a band gap of 0.7 electron volt. These are semiconductors. So remember that the crystal structure of silicon is, for example, diamond structure. You would normally think that this should be an insulator, but because it has a small band gap, it turns out to be a semiconductor. So the rule of thumb is that if the band gap is less than 2 electron volts, it would be a semiconductor at room temperature. Having said that, there is an important remark: all semiconductors become insulators at low temperatures. So this can be summarized by looking at the energy bands in the extended scheme. For example, you can see here that so in one direction, let's say we are plotting in a three-dimensional crystal the energy band diagram, and you can see if you have an even number of valence electrons, you have a completely full valence band, and the band above it, which is 2Vg, which has a 2Vg band gap at the zone boundary, is completely empty. So if the thermal energy is not high enough to excite electrons from the valence band to the band above it, which would be the conduction band, this would be an insulator. If we have an odd number of valence electrons, then we would have basically a complete, so in this example we have a completely full valence band and a partially full conduction band above it, and this would be basically implying that we have states for electrons to move into, so this will act as a metal. On the other hand, if we have an overlap of bands at a certain direction in a crystal, we can see that we have a partially filled and partially empty band. So there's a small band overlap, even though you have an even number of electrons per primitive cell. This may be the case, but you have very few electrons to contribute to conduction. Then this would give us a semi-metal. And the other scenario is that there is a band gap, there is a completely full valence band and completely empty conduction band at 0 Kelvin. However, at a finite temperature, this band gap is comparable to the thermal energy, so electrons can be thermally excited to the band above them, allowing conduction to occur. So this gives us a semiconductor. Okay, so to summarize, we have solved the central equation near the zone boundary. We have found standing wave solutions at the zone boundary, and we discovered that since we have the von Laue diffraction condition satisfied at the zone boundary, this is due to the diffraction of the interference of waves, electron waves at the zone boundary, giving us the standing wave solutions. The standing wave solutions give us basically two solutions with two different energies. One close to the lower energy one is when the electron is close to the ion core, and the higher energy one is when it is in between the ion cores. And we can see that this energy difference between these two solutions gives us the band gap at the zone boundaries. So these two solutions basically give us the forbidden zones at the zone boundaries. You can see here, we can look at this in the reduced zone scheme, or we can look at this in the extended zone scheme. So as for the number of orbitals in a band, if we look at the number of different k values we can have in the first Brillouin zone, it's actually capital N. Capital N distinct values of k with the spin degree of freedom included 2 for spin up and spin down gives 2n independent quantum states for electrons. That is allowed by Pauli exclusion principle. So this tells us that if we have an even number of valence electrons per primitive cell, then the solid can be an insulator. If we have an even number of valence electrons per primitive cell, but there is a band overlap, it can be a metal. If we have an odd number of valence electrons per primitive cell, it is definitely going to be a metal. So that's the three-dimensional case. If the number of valence electrons is odd, as we said, it's going to be a metal. But then there are materials that have an even number of valence electrons per primitive cell, but the band gap is small. It's less than 2 electron volts at room temperature, so which means electrons can get thermally excited from the lower bands to upper bands, and that gives us semiconductors. And all semiconductors are insulators at low temperatures. So these behaviors can be understood really well by looking at these energy band diagrams in K space. So instead of looking at a one-dimensional crystal, so if you look at, for example, a three-dimensional solid in a certain direction, you would also see these bands. And if you look at the band minimum and band maximum at the first brilliant zone boundary here, you can determine if it's going to be an insulator or semiconductor by looking at if the band is completely full. So the condition is that we need to have a completely full band, valence band, and we should have a large enough band gap for the material to act as an insulator. If we have an odd number of valence electrons, then we will have a partially filled band. So it's going to be a metal. There will be states for the electrons to move into. On the other hand, if you have a band overlap and with a small number of electrons occupying states in the upper band, when we have a small number of empty states, then we will have few electrons contributing to conduction. It would be a semi-metal. And if we have a small band gap where thermal excitations can cause electrons to move into empty states in the upper band, the material acts as a semiconductor.